look at now how one dimensional NMR spectrum can be interpreted, what are the different parameters. As I said, this is a course on for biomolecular NMR. So, the idea is to basically introduce very basics of these two concepts of chemical shift and coupling. We will not go into details which we have looked at in the previous course. So, let us briefly look at how this chemical shifts are calculated and how does spin-spin coupling affect our spectrum. So, chemical shifts, if you look at a 1D NMR spectrum in general or any NMR spectrum, these are the 4 parameters which you will notice in the spectrum. Firstly, the most important is the chemical shift, which is nothing but the position of the peak, and that tells you the information on whether it is an alkane, it is an alkene, or it is aldehyde and so on, or it is an amide and aromatic groups, etc. So, the chemical shift is the most important parameter. It tells immediately about the possible functional groups or structure of the molecule. So, that is what is the first thing to look at. The second is integral, that is how strong is the peak, and that number, the integral, gives us the relative number of protons or hydrogens as we saw in the previous class. Here we look at the area of the peak, and that is why it is called integration. In proteins and biomolecules, this plays a very important role because many of the quantification applications require this value to be correct. And the third thing, which is what is called as J coupling or spin-spin splitting, is because of the coupling between the hydrogens and the carbons, or hydrogens and hydrogens. This is basically the same thing as the fourth parameter here. The spin-spin splitting and coupling constant essentially tells you about what are the adjacent hydrogens and carbon present in the molecule, and it is a very important parameter as far as structure is concerned, because from the coupling constant or from the spin-spin splitting pattern we immediately get to know what are the number of neighboring hydrogens, whether it is a quaternary carbon, it is a tertiary carbon, and so on. So, we will look at this chemical shift little bit in more detail now and see how this is calculated. So, what is the first, why does the chemical shift arise in a molecule, and this is something which was briefly covered in the previous class. It basically, what happens is you have a nucleus sitting in the center of an atom, and an atom consists of electron cloud, and this electron cloud, which is basically not a single electron, it is a cloud of electron that tries to oppose the magnetic field at the center of the nucleus, and therefore, the magnetic field experienced by the nucleus is not just B0, it is reduced by some factor, and this is why we use the word shielding. So, essentially this electron cloud is trying to shield the nucleus from the external magnetic field, and that depends now on many parameters, how much is the shielding, what kind of type of shielding, is it uniform, and so on and so forth, and that depends on the structure of the molecule, it depends on many other properties. So, this shielding factor is a very small deviation from the main, from 1. So, it is not that the shielding is very high, the shielding just is a very small number, nevertheless a very important number. Without this shielding we would not be able to do NMR at all, even though we have all the possible of, we have the nuclear magnets and so on, even then without having this shielding effect NMR would have been not usable. So, therefore, it was very important to understand this chemical shift concept. This is the heart of the NMR technique as far as structure is concerned. So, we can see this what determines the shielding, how much is the nucleus shielded, that we will see the factors as we go on. But now let us see how it is chemical shift value, that is how much is this shielding value calculated based on these parameters. So, now they can see here again, remember this equation. So, we are looking at an effective magnetic field which is now different from the main magnetic field because of this factor. Now, this can be positive or negative. We will for example assume time being it is a positive, sigma is positive. So, this is smaller than 1. So, this is how it depicted, the chemical shift effect is depicted here. So, you can see that because of this shielding factor, the energy gap for the CH3 becomes smaller than the energy gap of CH2 and smaller higher for the OH, because this is the least shielded, this hydrogen is least shielded because of the oxygen here. We will see this concept of inductive effect shortly, but because of less shielding the energy difference in the alpha and beta states of this hydrogen, this proton, is high compared to this and compared to that. So, now this energy difference depends on, now remember delta E is h into mu. So, the mu, that is h into mu, the mu value, the frequency value changes for this, changes for this, and changes for this, and that is why these 3 different atoms or hydrogen comes at different frequencies. and that frequency is converted into a scale called as ppm scale. So, essentially what is going on here is that each hydrogen atom is experiencing a different frequency of resonance. They are not resonating at the same frequency, they are experience different resonating frequencies, but they are converted into a scale which makes it independent of the frequency scale. We will see that shortly how this comes about. So, this is how the calculation is shown here. So, essentially the main thing is the chemical shift value when we calculate in ppm scale is based on a reference and it does not change with field strength. This is a very important parameter. That means, if I go from 300 megahertz spectrometer to a 700 megahertz spectrometer and take the same molecule ethanol or any other molecule, its chemical shift value in ppm should not change, and that is why that has happened. That comes from this formula or calculation shown here. So, let us say that we have a reference frequency which is our rotating frame frequency, and that is standard B0 gamma into B0, and that is the precessional frequency of a reference nucleus. Okay, so, we can take any nucleus as a reference and assume that it has 0 chemical shift. So, remember this is an assumption. Many a times people are confused that reference molecule has actually 0 chemical shift. No, we are setting it, forcing it to be 0, and it is an arbitrary. So, let us say that reference has frequency is has chemical shift 0. So, it has a perfect condition resonance shown like this. Now, our proton of interest is not having a 0 frequency, it is having a finite chemical shift value, that is not 0. So, its frequency now will be like this. So, what we do next is we can subtract these two. So, when we subtract these two and divide by gamma B0, you can simply do yourself this calculation, you will get this sigma in this way. So, this sigma, that is a chemical shielding factor, chemical shift or shielding factor, is now mu minus mu reference divided by mu reference. So, what is mu reference? Mu reference is basically the magnetic field strength, which remember was in 10 to the power 6 in megahertz, and this is the difference between the frequencies. So, what happens is now, since mu ref is in megahertz range, the value of sigma will become 10 raised to minus 6, because this 10 raised to the power 6 goes up to the numerator as 10 raised to minus 6, and therefore, we use the word ppm. So, sigma becomes in the order of 10 raised to minus 6, and that is why we use the word parts per million or ppm. So, what happens is, because you are subtracting reference frequency and again dividing by the reference, the chemical shift value, the shielding value in ppm scale becomes independent of the frequency, that is, it becomes independent of this number, whether it is 700 or 300, because you are dividing it by that number. So, it is kind of scaling. So, that is shown here. For example, let us say I have two frequencies. So, the question here is how much is the difference if two nuclei have 1 ppm difference in chemical shift value. So, let us say one chemical shift value is sigma 1, which is given by this, which is same as the formula in the last slide. Another proton is having another chemical shift value, which was again is same formula, except that only thing which is changing here is mu 1 and mu 2. So, you can see that now if I subtract the two, the difference I am considering as 1 ppm, which is what was shown here. So, that is 1 ppm means 1 into 10 to the power minus 6. So, therefore, if I subtract these two frequencies sigma 1 minus sigma 2, then if you look at this equation, if I subtract this, what will I get? I will get mu 1 minus mu 2 divided by mu ref. So, the mu ref, it goes to this side, that is how it is written here coming from these equations. Now, that is 10 to the power minus 6 is this number, and that multiply with 500 into 10 to the power 6, because let us say we are at 500 megahertz. So, if you go to 500 megahertz spectrometer, if the 500 megahertz spectrometer is used, then you are now the difference in the two frequencies, which are only 1 ppm apart, now the difference actually is 500 hertz. So, you see the difference now actually depends on the frequency, the spectrometer frequency, but that is in the hertz scale. In the ppm scale, they are still 1 ppm. So, suppose I go to 900 megahertz spectrometer or 800 megahertz spectrometer. If I do the calculation there, again the difference will remain the same, they are still 1 ppm away from each other, but in the hertz scale this number will become 800 megahertz. So, 800 will come here and this will become 800 hertz. So, you see the difference in chemical shift value between two peaks definitely changes in a Hertz scale it becomes 700, 800 depending on the spectrometer, but its difference in the ppm scale will always be constant. So, that is the beauty of a chemical shift scale, that it does not affect the chemical shift value in ppm scale, it affects only the chemical shift value in the Hertz scale. That is why chemical shift scales are very popularly used. So, this is what is basically shown here, is because of this term here mu ref, which came from the previous equation or previous slide. Mu ref changes with field strength, that mu ref is nothing but this term, and this is depending on your B 0. So, if your 500 megahertz has one B 0, 800 megahertz will have a higher B 0. So, the reference frequency definitely changes with spectrometer. So, therefore, when you calculate in Hertz scale it changes, but what does not change is the difference in the ppm scale. So, you can see this is what is depicted here, that if you take in a Hertz scale, so this left side is frequency scale, frequency meaning in Hertz scale, and the right side is the delta scale which is in ppm value. So, you can see two peaks or a set of peaks always remain in the same, whether you are at 250 megahertz, at 500 megahertz or at 750 or 900 megahertz different spectrometer, the peak pattern, the three peaks will not change. But now if you calculate the difference between the two, the peak, let us say green and this blue peak, their difference is not same, they are actually changing and they are linearly increasing because of this frequency changes, because of this magnetic field change. So, you see the difference now, the difference is that although they look same in the delta scale, they are actually at the frequency scale, the Hertz scale, they are not the same, the chemical shifts they are actually changing. So, therefore, ppm scale is a very preferred scale because it makes it independent of the spectrometer that you are using, and therefore, it is very handy and useful to use, whereas Hertz scale tells us that they are going apart. So, the resolution, you see the resolution is going up because I am separating the peaks more and more. So, as you go higher and higher magnetic field, it is not that the chemical shifts are not changing, they are changing in Hertz scale, and that helps to increase the resolution, and that is one of the reason why in biomolecules there is a lot of effort to go to higher magnetic field, because the resolution is improving as we go up, and this resolution linearly goes up, and therefore, it is very useful to have a Hertz scale or higher frequency for biomolecules. So, what are the different factors which affect the chemical shift? So, this is just now we alluded to one factor, which is the effect of inductive effect, but we look at quickly through all this. Again, this is something which has been covered very nicely in various textbook in the previous course, but we will have a quick glance, because in biomolecules all of this have an effect, and therefore, it will be useful to understand the effect, how they affect the spectrum. The first one is the simplest effect, that is the inductive effect, and that is nothing but related to the electronegativity. So, you can see a very simple drawing here, that if you have a carbon, a molecule in biomolecules we do not have chlorine, but let us take an example of some molecule which has a carbon attached to this chlorine. So, because of this electronegative atom, which is highly electronegative, it pulls the electron from the carbon, and therefore, the electron density, how the electron cloud is distributed changes, and therefore, that in turn changes the electron density around this proton. So, this proton is also affected indirectly because of the electronegative effect of this chlorine. So, this can happen with other electronegative atoms like nitrogen, oxygen, carboxylate groups and so on. So, therefore, what chlorine essentially is doing is it is de-shielding, it is taking away the electron from the hydrogen. So, therefore, hydrogen becomes partially positively charged, and by taking away the electron density from hydrogen, it is reducing the shielding factor, the sigma value which we saw in the previous slides, it is reducing, and that makes it go closer to as much as de-shielded as possible. So, that is one of the simplest effect, and this is shown further here for some alkyl halides. So, you can see fluorine we know is the most electronegative atom. So, that has the highest de-shielding effect on this particular hydrogen. So, you can see that therefore, it becomes very high chemical shift, de-shielded, it goes downfield, that is to 4 ppm, and as you go lesser and lesser electronegative atoms, the de-shielding effect is reduced, and you can see that it is going low. So, the tetramethylsilane, which is the least de-shielded or most shielded, is the reference which we normally take it as 0. Again, remember, this is not that chemical shift value is 0, we are forcing this peak to have a 0 value. With respect to that, we are actually calculating the others. There is an arbitrary 0 concept, arbitrary reference which is put as 0. So, you can see the shielding effect is very clear, very linear with respect to the inductive effect. Now, this is another example where we have taken a little bit away. So, you see this is a little higher second order, in the sense it is not directly attached to an electronegative, it is away from the electronegative atom, one by one hydrogen here. So, this is the second hydrogen away from here, this is directly attached, and whereas this is 2 carbons away, this hydrogen. So, you can see the effect is reduced, for this which is closest to bromine has the highest shielding effect, shielding effect, and this is the less de-shielding, and this is the most shielded. It is it is very away from Br, that is bromine. So, therefore, it is having the least de-shielding effect. So, this is something which all of us are aware of. This is just bringing this. The second factor which also helps inductive effect is the number of electronegatives. So, you can see in chloroform you have 3 carbons, which is 3 chlorines, sorry. So, 3 chlorines have the maximum de-shielding effect, and therefore, this hydrogen is highly shielded compared to this hydrogen, compared to this which has only 1 chlorine. So, these are the basically different de-shielding shielding effects. Now, let us look at this concept of chemical equivalence, and this is also a very important concept. So, chemical equivalence basically means any 2 hydrogens, if they have identical chemical environment, they will end up with the same chemical shift value. Now, having chemically equivalent is basically means same chemical shift, but same chemical shift need not mean chemical equivalent. So, the reverse is not true, which is written here, that 2 nuclei may have accidentally the same chemical shift value, they cannot be considered as chemically equivalent, because the above condition has to be satisfied. So, you see here there is a condition, very important condition, these 2 hydrogens should be interconvertible in their positions by symmetry operations, which means I should be able to take those 2 hydrogens which are equivalent, having the same chemical shift, and if I change their replace one with other, it should have the same symmetry in the atom, in the molecule. So, let us look at the case here, is shown here. Look at this molecule here, it is basically has a rotational symmetry. So, you can look at these 3 hydrogens, if I rotate it and this hydrogen comes here, this hydrogen goes here, it does not affect anything, it remains, these 3 hydrogens are kind of chemically equivalent, because they are all rotating and therefore, their positions are equivalent. It is equally distant from these 3, whether it is in this position or in this position or in this position. So, because of this rotational symmetry, because it has a rotation n-fold symmetry axis, these 3 hydrogens are equivalent. Similarly, we know the center of symmetry here, if this hydrogen is inverted, it has an inversion of symmetry, these 2 hydrogens have the same chemical environment and they are related by symmetry operation, they can be converted from here to here, here to here without any change in the structure of the molecule. So, remember symmetry operation basically means if you rotate or you take a reflection around any axis, it should not change the structure. So, that is what is shown here, these 2 hydrogens are chemically equivalent. Now, you can look at more examples. So, this is another case where there is a mirror, is an plane of symmetry, not an axis of symmetry. So, if you look at this plane of symmetry, these 2 hydrogens are mirror image, therefore, they are identical, they are equivalent, and therefore, that will not change whether I take this hydrogen here or here, the structure will not change. So, this is another example. So, we can keep having different examples. We will go to what is the most important is the methyl. So, methyl groups are known to be always strong peaks in NMR spectrum. In fact, in biomolecules methyls play a very important role, and we will look at the methyl groups as we go along. So, here these 3 hydrogens, why are they equivalent? There is no symmetry concept here, they are equivalent basically because they rotate very fast around this axis. So, you see this axis here, they rotate very fast around this axis, and because of that rotation they become equivalent, because they are average out in their environment, and because of this averaging they are essentially equivalent in the chemical shift. So, methyl groups always you will see in NMR spectrum are essentially a group together. So, they will be 3 times stronger or even more compared to any other protons in the spectrum, and they are very easy to identify. The second concept which is very important in NMR is a magnetical equivalence. So, we saw just now chemical equivalence. Let us look at an example here. So, if you see here this X, which is a hydrogen, this is some functional group, this can be another functional group. If you look at these 2 hydrogens, there is a symmetry here. If I draw a line here which is shown by this mouse, there is an axis of symmetry. So, you may say that this hydrogen is equivalent to this hydrogen and this hydrogen is equivalent to that hydrogen, which is fine. So, they are chemically equivalent. But if you look at this hydrogen, its coupling to this Hb here is not the same as its coupling to this Hb here. So, you see this is very far away, this is 1 bond, 2 bond, 3 bond, 4 bond away, whereas this is 3 bond away, 5 bond away in fact. So, you see this two hydrogens are coupled, J coupled, which we will come to shortly. Their coupling is not the same as the J coupling between this hydrogen and this hydrogen. So, therefore, although these two hydrogens are chemically equivalent, they are not magnetically equivalent because their coupling to the neighboring hydrogens is not the same. So, for example, the coupling of Ha to Hb is different from this Ha to this Hb. So, although A and A are same, they are A prime. So, this is a nomenclature typically used for denoting spin systems, which will not go into detail, but the idea is they are chemically equivalent. So, chemical shift will be same, but magnetically they are not equivalent. So, that does not affect much in the spectrum. So, we will not go into detail of magnetic equivalence, but what affects the most is a J coupling. So, which is shown here. So, J coupling essentially you see if you look at any NMR spectrum, you will never see a single peak, you will always see a multiple structures like this, and that is happens because of this phenomenon called J coupling or scalar coupling. J coupling has a very rich history and how it was discovered is very interesting. You can have a look at it in different textbooks how it was actually discovered and found out. So, we use different words for J coupling, sometimes in textbooks you will also use we use the word spin interaction, you will see the word scalar coupling and so on. So, J coupling essentially happens only when there is a covalent bond between two hydrogens. So, that is why we use the word through bond interaction. So, let us go through J coupling briefly. How does J coupling affect the spectrum? So, this is shown here as an example. So, let us say you have a spin system or a molecule like this. So, you have this carbon has two equivalent hydrogens. So, let us consider as chemically equivalent, and this is not this is one hydrogen we are looking at. So, in the NMR spectrum this hydrogen will be coupled to this hydrogen and this hydrogen, but because these two are equal or equivalent, this hydrogen will look at them as two equal hydrogens. So, its number of peaks for this hydrogen will follow a rule known as n+1 rule. Therefore, n is the number of chemically equivalent hydrogen to which this yellow color is coupled. So, it will now show as a triplet. Okay. So, the triplet meaning 3 lines. Now, the intensity of the 3 lines are not the same, but we will see that soon is using a concept called Pascal's triangle. Now, let us look at these two hydrogens. So, we looked at this yellow color here. Now, in the same molecule, let us say what happens to these two. So, these are chemically equivalent as we assumed. Remember, it need not be equivalent. In fact, in biomolecules, molecules like this, moieties like this are never equivalent. So, we will see that when we come to the biomolecule part, but let us assume that right now some molecule they are equivalent. In that scenario, these two are together as one entity. Now, this one entity is coupled to another one hydrogen. So, according to the n+1, n is equal to 1 because these two together are coupled to only one more, and that is a doublet. So, these two peaks, these two meaning one peak for these two hydrogens will show up as a doublet, and the peak for this hydrogen will show up as a triplet in the NMR spectrum. So, this is what is called as the n+1 rule, where only it applies when there is an equivalent hydrogens. Okay. So, we can actually see at more examples. Now, what happens if the coupling between, let us say we have two protons. So, this is all protons here. So, this is one hydrogen A, this is another hydrogen B. Remember, this is just a schematic drawing, do not think of it as a bond here, it is actually a CH, let us say, and there is another CH here, another CH here. Okay. So, this CH hydrogen in center is coupled to two protons. So, one proton this side and one hydrogen this side. Now, these two hydrogens B and C, let us say, are having chemically different environment. So, they will be having different coupling to this hydrogen here. So, which is written as J1 and J2. So, if J1 is equal to J2, then it will be a chemical equivalent case and it will become a triplet. But if it is not same, then how does the spectrum look? So, that is how it is analyzed here. So, you can take a particular peak here, that is without any coupling. So, let us say that C and B did not exist. If C and B did not exist, A would have no coupling and it will only have a single peak. But now it is coupled to these two hydrogens, one on this side, one on that side, and with different coupling values. So, in such a scenario, this peak first will get split it into two peaks. and it will shown as J1 here because of the J coupling, that is shown here. It gets shown, split it into 2, and each one of them is having a half the intensity as previous. So, remember J coupling simply splits the peak into 50-50. So, one peak is half, another peak is half of this original peak. So, it is 1:1. But then there is another coupling J2, and that further splits each of these peaks into further 2. So, you can see here now it has become 2 separate peaks. So, first it split into this dotted line here, and that each peak which was here further split it into 2 more. So, you will get what is called as a doublet of a doublet. This is not simply a triplet. A triplet would have come if they were all equal values, J1 was equal to J2, but because now the J1 and J2 are not the same, they become a doublet of a doublet. So, this is the scenario if the couplings are not equal, this is what happens. So, now the J coupling value between two hydrogens depends on varieties of factors, which is listed here. This is similar to chemical shift values. So, you can see that it depends on the gyromagnetic ratio, not ration, it is the ratio of the two nuclei. So, if there is a hydrogen and carbon, the J coupling will be different with compared to hydrogen and hydrogen, and hydrogen nitrogen will be different, and nitrogen carbon will be different, and so on. Similarly, it depends on how many bonds are separated. Remember, this is a through bond interaction, which means it depends on number of bonds separating them. If they are separated by more than 3 bonds, 2 hydrogens, then the coupling is very small. If they are separated by one bond, of course, hydrogen hydrogen one bond cannot come, it becomes hydrogen molecule, but you can have hydrogen carbon one bond, then it is a very strong coupling. And if you have carbon nitrogen one bond, it is also good, but if you have carbon carbon 2 bonds away, then it is very weak. It depends on the structure of the molecule, which is also we use the word conformation and very useful. So, these parameters are very important in biomolecules. So, one should remember these things, because this is how it will affect our sensitivity or the pattern what we will see in heteronuclear NMR, that in biomolecules, and depends on the hybridization state. For example, in aromatic the hybridization sp2, whereas in aliphatic in methyls it is sp3, and therefore, it depends on what is the hybridization state, the chemical shift coupling coupling spin coupling will also change. If you look at the substituents, again it matters. So, if there is a functional group OH compared to attached to C versus some other functional group, then the chemical shift, the coupling of carbon to protons will change. So, you see there are varieties of parameters which affect the chemical shift and coupling values. So, coupling here is shown for different types of combinations. As far as our biomolecular course is concerned, or this course is concerned, we are mainly interested in hydrogen to hydrogen. Of course, this is in a hydrogen molecule, not in a 3 bond hydrogen. You can see the hydrogen hydrogen direct coupling is very strong. We will not bother about this. This is just a highest value possible. But if you look at hydrogen to carbon, this is the range which we will be using in our biomolecular experiments, and we exploit this high coupling. If you look at phosphorus, which is in nucleic acids, that is also very strong. If you look at carbon to carbon double bond, it is also strong. Carbon to carbon single bond is also quite good. This is useful in biomolecules. So, in biomolecular NMR, all these couplings are very useful and exploited in designing various experiments. We will not look at fluorine in this course, because fluorine is not present in biomolecules. Fluorine is present in different chemical molecules, which is not part of this course. And finally, the one thing is how does the J coupling depends on the conformation. So, this is a very famous equation known as the Karplus equation. This says that a coupling between 2 hydrogens which are 3 bonds away. So, look at this picture here, they are actually 3 bonds away. So, if you draw this molecule, you can show like a book, like a 2 planes here. So, one plane representing one hydrogen, one carbon, this carbon, and the second plane representing this hydrogen, this carbon, and this carbon. So, you see now the angle between the 2 planes is known as this torsion angle, a very important parameter when it comes to biomolecular structure. So, the torsion angle, or also use the word dihedral angle, now is basically this angle, and therefore, and this coupling between these 2 hydrogens depends on this angle by this equation. The very famous Karplus equation way back in 60s was proposed, and it has this form. You can see this as a form like this. It is a cosine function, cosine square plus cosine. So, you can see if I know the J value, I can guess the phi value from this. Of course, it has multiple possibilities, but still I can narrow down what are the possibilities. Similarly, if I know the dihedral angle value, from there this plot, suppose I know it is somewhere like 140 degrees, if I go up here I can get the chemical shift, the J coupling of those two hydrogens. So, you see it is a interrelation or a connection between J coupling and the dihedral angle, which is very useful in biomolecules. It is worth repeating that. As we go along, we will see the alpha helical structure, the beta sheet, all depend on this J value, which is useful. So, we will in the next class we will look at the final aspects of 1D NMR, which is C13 NMR, and look at a very few practical aspects, and then we will go on to 2D NMR.